So last time we did this. How to draw a histogram, convert count to percent if necessary. So I say if necessary because sometimes the data will already be given in percentage terms. So then you don't need to, you don't have the counts. You literally have the percents already. Then for each bar, find width and height, draw and label the axes, and then draw on the bar. So I did an example last time. I'll just put it on there again. Here's all the data for it. And it's data on you. I kind of changed it a little bit just to make the numbers come out nicely. But so here, I collected the data in terms of number of counts. How many people are in each of these groups? And incidentally, these groups are called class intervals. Okay? There's one class interval for each line here, right? Each category. So you fall into one of these class intervals. Okay? So these 5 class intervals, I counted how many people in each one. First step, converting that to a percent. So I could have, and some problems in the book, a lot of problems in the book actually, will start here. The data is already given in percentage terms, so you don't have to do that first step. OK, so once you get the percents, calculate the widths, then the heights. So the widths are just the widths of each of these class intervals. So this one's 200 wide, 200 wide, 200 wide, right? 400 or 600 minus 400. This one's 400 wide. OK, width is 400. 1,000 minus 600. And then the last one's, 1,000 wide. OK. So those are the widths and then the heights. So the heights are percentage is in area in terms of areas in terms of percents. So the area of one bar is equal to the width times the height. Okay, they're all rectangles. So width times height equals area. And to get the height, then you take the area divided by the width. So this, if you want to check it, is 43.3 divided by 200. Is equal to 0.217, and so forth. OK? OK, so that's steps 1 and 2. So I thought I'd put all the math up there ahead of time so I don't have to rewrite it. Steps 3 and 4 are to draw the histogram itself. So draw and label the bars, monthly cell phone usage in minutes. So I did this last time too, so you might still have this in your notes from last time. So 2, 4, 6, 200, 400, 600, 1,000, and 2,000. Okay. And then the y-axis is slightly strange units. So this is 0.1, 0.2, 0.3. percent per minute, and I'll talk a little bit more about those units in a second. First bar, 0.217, somewhere around there. 0.167, 0.083, 0.008, and 0.003. OK. So roughly that's the picture for the histogram. Right? Step 3, draw the bars and label them. Step 4, to draw in the bars. OK. So I kind of finished that a little bit hurriedly last time. Any questions about that? Yeah? I don't think it actually says that. You can if you want. It doesn't matter. Yeah. If you want, you can. He's just saying you could put the axis off a little bit if you wanted to. I don't really care. Okay. So if you do that, then this axis would just be a little bit to the left of 0. Up to you. It's sort of a style point. Yeah.
If I add one more person who uses exactly 200 minutes, will 130 become 131 and 100 become 101?
OK, so good. There's what's called the left endpoint convention. And the left endpoint convention says that the bars contain the left endpoints but not the right. So 200 is in the second bar. 200 is in the bar from 200 to 400. This bar contains 200 because it's the left endpoint. This first bar from 0 to 200, it doesn't contain the right endpoint. It does not contain 200. So if you talked on the phone for exactly 200 minutes, you'd be in this second bar. In practice, one way to think about why that's true, a couple of reasons why you might think about why that's true. One is that for something like minutes, just like with age, if you are, say, 20 years old and you're about to turn 21, you're 20 years old until kind of midnight going into your birthday, right? So you're sort of 20 and then you're 21, okay? So same sort of thing here. If you're talking on your phone, you've talked for like 199 minutes and 59 seconds, and then as soon as you hit 200, you're jump into this bar, okay? So anything, having to do with time, I think sort of naturally does that, right? If you 11:59 a.m. and 59 seconds, it's still before noon until you hit noon. As soon as you hit noon, clock changes 12, okay? So sort of think about that in terms of these things. That's, I think, one reason why it's sort of natural to have it not quite, 200 is not quite in that bar, it's in the next bar. As soon as you hit 200, you're in that bar. Another reason why that sort of makes sense is you think about 0 to 200, if you sort of think, well, if we were to sort of think about whether or not we'd like to have a left endpoint convention or a right endpoint convention, if you had this first bar, 0 to 200, if that bar did not contain 0, then what would you do with someone who talks 0 minutes? They're not in that bar, right? If the bars included the right endpoint but not the left, then 0 wouldn't be in there. What would you do with them? Well, you sort of need to make another bar. You would sort of need to make a bar here, and that bar would look kind of stupid, right? It's sort of negative, would sort of look like negative minutes. So that's another reason why it sort of makes sense that you want to include the zeros with that first bar. Okay, so kind of two kind of logical reasons why you want to adopt the convention in that way. Okay. Yeah. Okay. So maybe I'll stop there. Yeah. Yeah. So choosing the class intervals is sort of arbitrary. You sort of, the smaller you make the class intervals. If I did like 0 to 100, 100 to 200, whatever. If I made them even smaller, like 0 to 10, 10 to 20, you get more detail, right? Your picture includes more information in it. This picture loses a certain amount of detail that I can't quite tell exactly what's happening within each of these bars. But if I did that, first of all, if I did it in class, it would take a long time if I make lots and lots of bars. So from a practical consideration, you sort of balance that. There are kind of these arbitrary rules that people make up about ways to choose how many bars you want to have. I'm not going to discuss that. I don't really care. I don't think I'll ever make you decide how many bars to use. Every problem in the book certainly has, I'll just say it. I won't ever make you decide. I'll give you the class interval somehow, or the problems in the book, we'll give them to you. Okay? But sort of about this many, or maybe a few more, gives you a reasonable amount of detail that you can see something about the data. And really that's the point, is that anytime you're making a histogram, you'd like to see something in the picture that you wouldn't be able to see without it. So in this picture, you sort of see a lot of people here, and then it sort of dwindles off. There are a few out here, but not so many. Yeah.
The text mentions that a histogram doesn't necessarily need like a vertical axis. So when would you need one, and why? How would you determine that?
Okay, so he says, the textbook says that you don't really need a vertical axis. I will always require you to make a vertical axis for any problem that I assign. Quiz, homework, exam problems. The sense in which you don't need an axis is that it's sort of implied by the fact that the bars, let's say it. So this sort of fundamental fact about histograms, area is percent, so total area is 100%. So if I didn't tell you that, if I didn't give you that bar, you should be able to figure out what it would have to be. Because since the total area is 100%, if I take this distance here, 200 times the height, I could figure out what percentage is in there. And I could do that for every bar. Okay? I could figure out what percentage is in each bar and then figure out what the axis label must be. Even if I didn't have these labels, even if I didn't have numbers there, I couldn't quite, for this example, the numbers didn't quite come out so evenly, but in theory, I could like take a ruler and measure and figure out, well, if I have width here times this distance, width here times this distance, I could figure out what distance, like what number would have to go here in order to make the total area 100%, right? If I change this to something else, then the bars, the area of the bars is not going to add up to the same thing. So in a sense, you know, this is a little bit unnecessary, because if you wanted to, you could always figure out what it is. But certainly, I think it's easier to read if you do label it. And like I said, I'll always ask you to label it, sort of more clear that way. Okay? Yeah.
If you want to keep the interval it's the same, because right here you have 200, 200, 400,000.
Yeah.
So wouldn't that give you maybe not a totally accurate representation?
So his question is, wouldn't you want the bars to have the same widths? And he's suggesting that might not be kind of accurate this way. Well, you lose a certain amount of information, but it's not, you don't lose any accuracy in the sense that, you know, it's still true. The reason why I did it that way is that there's not much going on from 1,000 to 2,000, you know? There aren't a lot of people, and so asking, okay, who talked between 1,000 and 1,100? Who talked between 1,100 and 1,200? 1,200 and 1,300? It's sort of a waste of time. There's just not a lot of people out there, so there's not a lot going on. So I'll discuss that issue a little bit more in terms of the axis label, why it is percent per minute and what that means. So maybe if I haven't satisfied you in 10, 15 minutes, then you can ask me more about it. Any other questions? Okay, so let's talk about, let's see if I answered already. Yeah, let's talk about why. Well, let's talk about the density scale. So this label on the y-axis is called the density scale. I'll just put that here. Okay, so density scale is what the y-axis uses as the units. Now, density scale is always percent per x unit, whatever the x unit is. So in this case, x units are minutes, so that's going to be percent per minute. And the reason why that is to sort of make it so that when you multiply the x value, the like width of an x value, so the width in x units times a height in percent per x unit, when you multiply those two things together, the answer is in terms of percent. Right? Multiply percent per minute times minutes, you get percent. And just as an aside, I want to talk about a case that you're more used to maybe. Percent per unit, or sorry, percent per minute might seem like kind of strange units. Let me do this quick sort of side example. This has sort of nothing to do with statistics, but a little bit to do with units. So suppose I drive 100 miles in 2 hours. How fast do I drive? Or did I drive? Anyone? Yeah, sure. 50 miles per hour. Okay, so how did you get that? Yeah, good. So 50 miles per hour. And the way to get that is to take 100 miles divided by 2 hours. Okay, let's think about these units here, miles per hour. Okay, when you divide units like this, that's what happens, right? So when you divide 100 miles by 2 hours, your units end up being miles per hour. How did we get the height here? To get this 0.217, what we did was we divided an area in percentage terms divided by a width in terms of minutes. So we're dividing percent 43.3% divided by 200 minutes. So the height is 0.217% per minute. Okay? So the same basic idea going on that gives us those units of percent per minute. Okay? So when you look at these units, miles per hour, this is like a rate, right? It's a rate at which I'm traveling. There is sort of a similar sense in which the density scale measures something similar. If I sort of imagine traveling along the x-axis, like, minutes, looking at the minutes on the cell phone, minutes of cell phone usage. If I'm in this bar, I kind of use up a lot of people quickly, or I pass by a lot of people quickly. Okay? So in a sense, there's sort of a lot going on. The people are dense here. Okay? So this y-axis kind of intuitively measures the density of the people. Out here, I pass people very slowly, sort of. Per minute, I don't get a very high percentage of the people. So for every minute I go, the percentage of the class is not very much. For every minute I travel here, I get a higher percentage of the class per minute. Okay, so that's the sort of the idea here. And it is a little bit, it's kind of analogous to this idea of speed or rate here. That if I travel more slowly, I sort of don't use up as many miles per hour. Or I don't go, get as many miles per hour. There's also a little assumption here I'm making to get that answer. What assumption am I making? Yeah, that I'm traveling at a constant speed, right? That I'm traveling 50 miles per hour, constant speed for 2 hours, which in reality it probably doesn't make sense. But sort of most of you probably thought about it that way. Maybe some of you thought, well, depends. But yeah, you at least sort of see that answer makes sense. Similar sort of thing is actually true here, that when I draw this picture, all the bars have flat tops, right? And so I'm sort of making the assumption that between 0 and 200, the density is constant. Just like there, I'm assuming a constant speed. So for each bar here, in this picture, I'm pretending like the density is constant along that class interval. So that's true for every bar. For any problem that we do in here, where you have these rectangular bars, it's fine to assume that. I do sort of want you to recognize that you are assuming something there, that it's not quite perfect. Okay. Okay. Questions about density scale? Okay. I guess I want to write one more thought about it, or a little bit more about it. Just kind of another analogy to think about. So the word the book uses is crowdedness. Or maybe the non-word the book uses is crowdedness, the term. Okay. So again, that's sort of saying in these tall bars, things are more crowded. And one way I like to talk about that is to think about those bars as being sort of like buildings. So more people fit in the tall buildings than in the short buildings. So if you imagine these first bars are kind of in the center of town or something, then as you go out into the suburbs or something, or into the country, then you get lower density of people, fewer people. Yeah, so it's more crowded in the center, less crowded towards the outsides. Now, why are we doing this? So there's one more thing I want to say about, let's see, I guess I'll erase the top. So I think part of what one of the people that asked me a question was getting at, as far as making these bars all the same width or not. So here I have them not the same width. Now let's think about why the density scale works with this case and what would happen if I made them the same width. Well, to answer that, I want to talk about why I use the density scale. And one thing that sometimes people suggest is, well, why not just make the heights in percentage terms? You know, these units, percent per minute, they're kind of weird. Why not just make the heights the percentages themselves? Well, let's think about what happens if we do that. So I'll do a quick example. Totally made up artificial data on income. And let's say I have 2 class intervals. So income, 0 to, this is in thousands of dollars. Let's say I just have 2 bars, one for the people that earn 0 to 50 and one for the people that earn 50 to 200. And let's say 50% of the people are in each group. So if we approach this as a histogram, we would find the widths. So first step I don't need to do, right? It's already in percentage terms. I don't need to convert a count to percent. I do need to find the widths and the heights. So the width here is 50. And in the second bar, it's 150. And that means that the heights are, for the first bar, this is area divided by width to get height. I get 1. And here I get a third, or 0.33. OK, so this is income in thousands of dollars. Thousands of dollars. And I'm going to go from 0 up to 200. And then maybe about here is 50. OK. Height here is 1. Down here somewhere is 0.33. OK, so here's a histogram. Okay. So I got the heights, draw and label the axes. Percent per $1,000 is the label of this axis. And then put in the bars. OK, so that's a picture, and it tells us something, right? It tells us that a lot of people earn 0 to 50,000, and then sort of more spread out here, less dense from 50 to 200. OK, what if we graphed the percentages themselves? If we graph the percentages themselves, if I put percent as the label here, 50 there, 50 here, 0, 50, 200. OK? So this is not a histogram. I don't like that picture, right? It sort of doesn't tell us what we want to know. What we want to know from this picture is kind of how are the people spread out. And density or crowdedness is actually, I think, what your brain wants. Okay? If you're thinking about a picture that represents what's going on, I think this picture does a better job of representing what's going on than that picture does. If you look at that picture, then it's sort of hard to tell what's going on without thinking about it. It sort of looks like, it's sort of flat. It's the same number of people everywhere or something. So that's not a histogram. If you made all the class intervals exactly the same size, the pictures are going to look the same. Okay? And you can if you sort of think about that, why that's true, then the labels will be different. But what the bars actually look like will be the same if all the class intervals are the same size. Because if the widths are all the same, then you take the percentage, you divide by the same thing every time. And so the relationship between the height and the width is just multiplying or dividing by a constant. So scale, the picture itself, like I said, the heights would look the same. OK? So that's a little bit of trying to justify why we do a histogram this way, why these units actually, I think, make sense. OK? Questions? OK, so that's that. OK, so I wanted to ask one more question about that picture. Yeah. I guess so. so about what percentage of the class uses their cell phones between 300 and 400 minutes? So, any answers? Yeah? About 17%, he says. 16 point something? Yeah. Might be less than 17 because there may be a trend going on. Yeah.
But your thing is, so you're saying from that data, we're trying to tell that,
Yeah.
but you don't know how the data is distributed within that interval, though. So, like, couldn't I want to be 200 and what, minutes?
Yeah, so he's saying, couldn't it be true? We say we don't know what's going on in that interval. So we don't know of those, 200 to 400, there are 100 people. We don't know if those 100 people are all sort of in the beginning or towards the end. We don't know where they are in that interval. Okay, so it's true, we don't know for sure. Okay, any other questions, comments, thoughts? Yeah. So right, so for that reason, it might be nice for us to get a little more detail, to get more bars in order to be able to answer questions about, sort of more detailed questions like that. But, sort of a trade-off, it's a lot more work. I mean, in the extreme, I could get a bar for every single number, okay? That picture would have like all these really, really skinny bars, okay? And that would kind of give you very detailed information. Each bar would contain like just 1 minute in it. So I'll say a couple things. One thing is there's a practical difficulty with that in a class like this for me to say, okay, a couple of reasons why it's practically difficult. One is I just would have to go through and say, okay, how many people, 1 to 2 minutes, 3 to 4 minutes, 2 to 3, 3 to 4, and could go through, it would take forever. But there's another thing, which is that you may not know, right? You can probably tell me which one of these groups you're in pretty accurately, okay? Maybe if you're close to one of the borders, you're not really sure. But probably a lot of what you would round things off. So if I did that, if I actually got a number for every single value along here, you'd have these probably weird spikes at like 100 minutes, 200 minutes, 300 minutes, because a lot of you would round, and so it would kind of, you would sort of want it to be more accurate, but actually in some ways it'd be worse because of that rounding issue. But if you actually had perfect data, that picture would actually, it would be more detailed. It would give you complete information for things like this. But, practically, maybe it's not so easy, or, the picture would be kind of messy to have all these little skinny bars. The picture here, I think, is a little bit nicer. You can kind of get most of the information very quickly from here. Okay, so any other comments, thoughts? Okay, so I said, along with my discussion of miles per hour, that here you're making this assumption, right, that you're driving at constant speed, 50 miles per hour, and in reality that might not be true. Same issue here, might not be the same density across that whole interval. It might not really be flat, but for purposes of solving problems for this class, I'll allow it. So I'll sort of allow us to assume that that bar really is the way that it's drawn, that it really is flat. However, I want you to recognize that that is not true, and to recognize what effect that would have on our answer. So let's talk about this. So 300 to 400. The numerical answer that was given was like maybe 17, maybe a little bit less than 17. Well, how do you get that? So how do you get an answer of 17 or a little less? Anyone want? Yeah. Good. So any other way to get it? Anyone else do it a different way? Yeah. Yeah. Yeah, yeah. So I'll give that second answer. Well, I'll give the first answer first. So one way to do it is to think, well, Okay, I want this area basically. Area is percent, right? So one way to get that area is to take the width, 100, times the height, which is 0.167. It's that second bar. Okay, so one way to do it is to say 100, I'll write it down in English first. Width times height equals area. And area is percent. So the width of that half bar is 100. Just 400 minus 300 is 100. Times the height of 0.167. Units here. Actually, I'm sorry. Let me write down the units too. 100 minutes times 0.167% per minute. And all the minute parts cancel, and we get 16.7%. Okay. The other way to do it is to take the area of 33.3 and to notice that this is half of that bar. So the first, that bar has a total area of 33.3. Divide by 2 is about the same, right? There's a little bit of rounding here one way or another, but those technically should be the same. Okay, so questions about either of those answers? Okay, so now in real life, do you think that's too high or too low? If I ask the class. Too high? Why too high? Sure, go ahead. Yeah, in general, there's a downward trend here. So you sort of think that of the people that are between 200 and 400, probably more of them are on the left side, probably fewer of them are on the right. There's sort of this thing going on. So if I really found out maybe something like this and like this, okay, that's sort of generally going down in this, what's going down over the whole picture, okay? So you might think that the answer that I get using this method is a little bit too high. Okay, so probably a bit too high based on overall trend. Okay. I guess I realize it might be slightly different people that are here today rather than Tuesday, but maybe I'll count real quick in class. So who actually would say 300 to 400? Raise your hand. 300 to 400. Wow, that's a lot less. 300 to 400. Okay, well, that's not working very well. Maybe 15 or 20 people raise their hands. Okay, so anyway, I think in theory that should be true. Well, let's see, how many people 200 to 300? Okay, so that's more anyway. Okay, so more people answered 200 to 300 than answered 300 to 400. So at least we can verify that the trend is true, even though I think it's way less than 100 people raised their hands total. Okay, so any questions about this? Any of this? Any of the histogram stuff? Okay, so that's, I think, a pretty good time for a natural little break. There's still a little bit left in chapter 3 that I want to talk about, but I'm done with this example anyway. Okay, so maybe 3 to 5 minutes. Okay, if you could start, oops. Okay, if you could start sitting down and. Okay. So the last part of chapter 3 discusses different kinds of variables a little bit. And I mentioned this actually a little bit last lecture. Okay. So we could split up. So when I say different kinds of variables, what I mean by a variable is sort of any kind of characteristic that pertains to each person, or if you're taking data on cars or houses or something else, maybe your subjects or your items that you're gaining information about don't have to be people, but just for simplicity, let's talk about people. Okay, so a variable is some characteristic that each person has that you might write down on a form or something like that. Cell phone usage would be one example of a variable. So I'm going to divide these into two big categories, qualitative and quantitative. So what do those words mean? Anyone tell me what quantitative, qualitative, what those mean? Yeah.
Quantitative is just like an amount, a number.
What about qualitative? Sorry? Colors. Well, what does it mean in general, though? Is there, yeah? A word or a phrase? Yeah, so an example would be like a color. Okay, so roughly this is things that we would describe with words. The quantitative side is stuff we would describe with numbers. Which one do you think we'll do more of in here? Quantitative, right? Okay. So quantitative things are things like cell phone usage, income, things like that, where we have an x-axis which is measured with numbers. Histograms work for qualitative things, not for qualitative things, right? There's no way to sort of do a histogram where the x-axis is like colors, someone said, right? Do you remember what I said last time as an example of what kind of picture we would draw for something qualitative? You remember? Pie chart, good, yeah. So if there are different categories, a pie chart is something you might use to draw a picture for something that is qualitative. So what are some examples of stuff that would go on this side, qualitative side? Like characteristics of you that you would describe with a word rather than a number? You raise a hand, or yeah. Race, yeah, yeah. Uh-huh. Race, blood type. Just to sort of say quality. Someone said, like, you might rate on a scale of like 1 to 5. So I guess some of you would be excellent, some, not so good. I don't know. I'm just kidding. Yeah, so this might not necessarily pertain to people, but to maybe responses on a questionnaire, I think is what he's thinking of. Yeah. Anything else? Common stuff? Yeah. Tall, short. So the variable I would describe as height. And height you might give a number for. You could sort of group it into different categories by words, but I'm sort of not inclined to write this here because I think in general when people talk about height as a variable, people would think about it as being quantitative. So let's see, like gender is a real common one, right? Okay, so these are good, like quick list of different qualities. Someone said color, so it might be eye color, hair color might be things. Occupation is another common one. All things that you would not give with a number, you would give with a word or phrase. Okay, so what about quantitative? This I'm going to further divide up into two categories. Discrete and continuous. Okay, so what do those words mean? Anyone want to, what's the difference between those? Up there, yeah. Yeah, so discrete is whole numbers, or it must be a whole number. Continuous would be things like, it could be expressed with fractions or decimals. Okay, so again, think about characteristics of yourselves. He mentioned number of children. Okay, as one characteristic is whole numbers, right? Anything else? Whole numbers? Number of classes you're taking? Yeah. What else? Anything else? Whole numbers? Yeah. Age. Okay, good. So there are a few I think that are a little bit hard to tell. If you were asked your age on a form, I'm sure you would report your age as a whole number. However, in a sense, the actual number of the amount of time you've been alive is continuous. Some number of years, months, days, seconds, whatever. So one way you might think about the continuous things is it's things that you could divide up kind of as finely as you wanted to, even though in general you might not choose to. So things like age, height, weight, these are things that you would typically say as a whole number, but you could divide them up as finely as you wanted to. So that stuff I'll put over there. This stuff you can't, right? There's some number of classes you're taking. You're not taking halves of classes. You don't have half children, right? So one kind of amusing example that someone brought up was, what about half brothers? If you have some number of, if you have number of siblings, you could have a half brother, but I would count that as a whole sibling, okay? So that it's consider it to be a whole number. Okay, another one that's over here in the continuous side that might not be totally obvious is income. You might report your income as a whole number of dollars, but you could divide it up. You might say, well, but it's a whole number of pennies. You can't divide up the pennies. But really, this is sort of, you would divide it up as finely as you could divide it up as fine. Oops, income. You could divide it up as finely as you wanted to. And let's think about why I'm talking about this. I'm thinking about this for drawing pictures. If I were to draw a picture for income, I would never divide things up as finely as pennies, okay, for the purposes of drawing a picture. If I'm drawing a picture for one of these, each one of these numbers is going to get its own bar, okay? And I would never draw a picture of income where each penny got its own bar, okay? So let me talk a little bit about, in terms of drawing histograms, what makes these two sides different. Okay, so for discrete histograms, the bars will be centered on the numbers. So I won't do class intervals like I did here, where I have ranges like 0 to 200, 200 to 400, like that. I'll just draw bars for each number, okay? And I'll discuss in a minute, you can, if you want to, kind of collapse a few different values into one bar. But typically, what we're going to talk about for discrete histograms is just this, one bar for each value. So my little example is going to be here on a number of pets. Okay, so this is totally made up. I'll talk a little bit why this is true in a minute once I give you the data. So I'll give it to you in percentage terms. Suppose we have a group of people, 40% of them have 0 pets, 30% have 1, 15% have 2, 10% have 3, and 5% of them have 4 pets. Okay, so again, you notice that these aren't intervals anymore. They aren't ranges. This is just like 0, 1, 2, 3, 4, whole numbers. Okay, now we can still sort of follow the same steps for drawing a histogram, but it's maybe not quite so obvious what the width should be. I'm going to make all the widths 1, and when I draw my picture, I think you'll see why. So since all the widths are 1, the heights are just 40 divided by 1. So they're all the same. 40, 30, 15, 10, 5. OK. So let's draw a picture. So I guess just back up a second. When you look at this discrete side, whole numbers, you notice that all those are numbers of things, numbers of children, number of classes, number of siblings. That's very common for discrete things, is that you're just talking about the number of something. So the units here are really pets, right? Or you might say animals if you want, but it's essentially this is the unit. It's the number of something. OK, so here I will move this over a little bit from the edge just so that my 0 isn't like right on top of the x-axis. If you want to have a gap in here, you can. It doesn't really matter. 0, 1, 2, 3, 4. And 40, 30, 20, 10. So this is percent per pet. Okay, the units here, like I say, are just whatever you're counting. OK, so now I'd like to, I'd like to make my picture look nice. The point of drawing a histogram is to draw a picture that tells you something about the data, it's easy to read, and sort of looks nice. OK, so the bar over 0, like I said, is going to be centered on that number. The bar for 0, corresponding to 0, is going to be centered on that number. And it's going to have a height of 40 and a width of 1. So to do that, it's going to look like this. OK, so the edge of this bar is halfway in between 0 and 1. Now, there's a way, there's some sense in which this looks a little bit strange because it overlaps to the left this negative region. Obviously, you can't have negative pets. But since it's discrete data, this is sort of the clearest way, I think, to easily read what's going on, right? If you have the bar centered on 0, this bar represents 0 pets. Okay? We have 30% for the next bar, 15, 10, and 5. OK, so there's my histogram. Now, if we did things the way we did up there for the cell phone usage, and we used the left endpoint convention, what would it look like? I'm not going to relabel all the axes and everything. I just want to draw the shape, right? The bars. If we did using the left endpoint convention, well, we know between 0 and 1 would include the left endpoint, but not the right. So 0 to 1 would include 0, but not 1. So we might draw something like this. So this, I think, is not so satisfying as a picture for this data. Because when you first look at it, you look at this first bar, and you look at the axis, you think, OK, this is everyone that earns between 0 and 1 pets. Well, so it doesn't make any sense, right? There isn't anyone that earns really between 0 and 1 pet. OK, left endpoint convention says it includes 0, but not 1. So this is really the bar that's for 0. OK, so you have to sort of, I think you have to, when you first look at it, think for a second about what that bar means. So that's not so nice. So that's one reason why we don't draw it this way. So instead of drawing it like this with the left endpoint convention, we'll draw the bar centered on the values themselves. And that's, I think, a little bit clearer. There's another slightly mathematical reason why we do this like this. And I think I'm going to talk about that. I might get to it today. I want to sort of talk about it in conjunction with talking about chapter 4. So just keep in the back of your mind, there's another more mathy reason why I want to center the bars on the numbers. But just in terms of the visual picture interpretation, I think it's sort of nicer to have the bars centered on the numbers here. OK, questions about that? Comments, thoughts? Yeah. Well, I've just made up this data, and this is 100%. So I mean, in this data set, no one has more than 4 pets. If there were anyone else, then yeah, I'd have to draw more bars. But yeah, actually, the book has some examples where they do things like they make the last bar 4 or more. So they just say, OK, if you have more than 4 pets, we'll stick you in that last bar. So I do want to make one more comment about this, which is that it's not absolutely necessary to have 1 bar for each number. If you wanted to, you could make the last bar 3 or 4 pets. And you wouldn't, so you sort of can't set, if you have this bar 3 or 4 pets, what you would do is basically this. Actually, I'll erase it and redraw it. So what percentage of everyone has 3 or 4 pets? 15% of everyone has 3 or 4 pets. I would have a width of 2. So if I redrew this last part as being 3 to 4, 15%, width of 2, and the height there would be 7.5. Okay. So if I did that, then I'd have a bar like this. Okay. So there's 3, there's 4, and left edge of that bar is 2.5, right edge of that bar is 4.5. So it sort of encompasses both the 2 bars that used to be there. So that's okay, that's legal for a discrete histogram. For this case, it's sort of not, there's no point, and there you really do lose some information, right? We were talking about for continuous histograms how maybe it'd be nicer to have a few more bars so we wouldn't lose as much detail. And in this case, it's true, we sort of lose a considerable amount of detail for no good reason if we do it that way. It's sort of nicer to just leave it as 10 and 5, okay? But technically you can do that. And I think there are a few examples in the book that do that. The last bar is a couple of values stuck together. Okay, other questions, thoughts? Okay, so that's, let's see, I think last thing I wanted to say in chapter, yeah. That's the end of chapter 3. And so chapter 4 gets on to summary statistics. Chapter 3, histograms, that's all about pictures, right? Graphical, descriptive statistics. And last lecture I mentioned that descriptive statistics in general you can kind of break into these 2 categories: graphical, pictures, and summary statistics. So we'll talk about the average, the median, and the standard deviation in some detail. This is chapter 4. It's the average, also called the mean, median, and standard deviation. I think today I'll have probably time to talk about everything I want to say about the average and the median, but I don't think I'll get to the standard deviation. Okay, so let's just first think about definitions for these things. Both the average and the median are just conceptually measures of center. Like roughly sort of what's in the middle, what's the middle value. Okay, so the way we define them is that the average is found by taking the sum of all values and dividing by the number of values. Okay, so just add them all up, divide by how many there are. The average also has the characteristic of being the balancing point of a histogram. Okay, so what do I mean by that? What I mean is that if it's too bad I erased that, I guess I could have used it, but if I tried to imagine the histogram as a solid object, like all the bars are, I don't know, stacked bricks or something like that, and then I try to balance that stack of bricks, the average is where that should balance, okay? So maybe this one balances, I don't know, around 1.5, maybe a little bit less. Okay, somewhere around there. So that's kind of an intuitive idea of what the average does in terms of the picture. Okay, so let me do a couple of examples. Oh, I'm sorry. Let me define the median first. So just a rough definition. The median is a little bit harder to pin down in a way. So intuitively, half of the values are on each side. Okay? So that actually turns out to be different than the balancing point of a histogram, and I'll explain why in a bit. But I think I mentioned last time that if I wanted to find the median of the heights of all the people in the room, I could line everyone up from shortest to tallest, find the center person, and that person would be the median. Okay? So you notice that it's not really necessary to like collect a bunch of data or anything to find the median. If I just put everyone in order and take the middle person, that's enough. I can find the median that way. If I wanted to find the average of everyone in the class, I actually have to write down everyone's height, add them all up, divide by how many there are. So there's a sense in which this is easier to find than the average, but it's a little bit harder to give a technical definition of what the median is. Technical definition here is just like I said, take the sum of all of them, divide by how many there are. So a little bit more technical definition is that at least the half of the numbers or values must be less than or equal to the median. And at least half must be greater than or equal to the median. Okay, so it takes a little bit to write down. And that's almost complete. There's one more thing I have to add on to make it really work for all situations. And this, I think, what I'm about to write down maybe won't make sense until I do an example. Hopefully this makes sense before I do an example. But yeah, the last bit is that if so if multiple values satisfy this, take average of middle two values. Okay? So like I said, that part probably doesn't make sense until I do an example. So let's do an example. So first I'll do a sort of straightforward one. Okay, so my numbers are 1, 3, 4, 5, 7. To calculate the average, one plus 3 plus 4 plus 5 plus 7. Add them all up, divide by how many there are, which is 5. So 1 plus 3 is 4, plus 4 is 8, plus 5 is 13, plus 7 is 20, right? So 20 over 5 is 4. So the median. So if you sort of imagine my visual example of like lining up all the heights of the people in the room, this is basically, well, they're already lined up. I just take the middle value. It's a 4. Okay? If you want to think about that in terms of my more technical definition, at least half of the values are 4 or less. Right? 3 out of the 5 numbers are 4 or less. 3 out of the 5 numbers are 4 or more. So 4 works, and it's the only value that works. If I took anything bigger than 4, right, if I took something in here, well, it's not true that at least half of them are like 4.2 or more. So 4.2 would not work as a median. If I take 3.7, it's not true that it's not true that at least half of them are 3.7 or less. Only 2 out of the 5 are 3.7 or less. So nothing else works except for 4. So 4 is the median. Okay. So why am I making all this like noise about that last bit or like multiple choices or multiple values? Well, what if we have this? If we have 1, 3, 4, 5, 7, 10. The average is equal to 1 plus 3 plus 4 plus 5 plus 7 plus 10. Divided by, now there are 6 numbers. So 20, the first 5 numbers, that sum is 20, plus another 10 is 30. Divided by 6 is 5. OK, so the average is still easy. That's 5. Well, what's the median now? So if you think about it, anything I choose between 4 and 5, it's true that half the numbers are less than that, half the numbers are more. So like 4.2, at least half of them are 4.2 or less, at least half of them are 4.2 or more, so that would work. 4.7, that would also work, right? Anything between here would kind of satisfy the first part, okay? At least half the values are less than or equal to anything between 4 and 5. At least half of them are greater than or equal to anything between 4 and 5. So if I just left it there, I'd sort of be unclear what the median would be. So that's why I have this part. Anything between 4 and 5 would work. So if multiple values satisfy this part, take the average of the middle two values. So the median is 4.5 here. Take the middle two values, divide by 2, 4.5. Okay? So that's why I need that last bit. So, questions? Yeah. At least because it's not necessarily exactly half, but it has to be at least half. Like for this case, 3 out of the 5 numbers are 4 or more. So it has to be at least half of them, but it might be more. Okay? If I just said half of them, it might be a little bit vague because, well, it's not exactly half of them, but yeah, it has to be at least half. Okay? Any other questions, thoughts? Are these clocks fast? No. Okay, just wondering why. Seems like people are getting ready to go. Okay, so let me do a couple more examples. Actually, I'll erase this. Yeah, for some reason the clock there and these clocks don't quite agree. But what's actually true? That's not, even that one's a little, I guess that one's a little bit fast. I think these are a little bit slow. Okay. So let's see, that. Okay, so let's do one more that's sort of like these. Okay. So I'm starting with the first set of numbers, 1, 3, 4, 5, 7. I'm just changing the 7 into a 12. So 1 plus 3 is 4, plus 4 is 8, plus 5 is 13, plus 12 is 25. So 25 over 5 is 5. And what's the median? Still 4. Okay, so we noticed something about the median here, which is that the median doesn't change if you change extreme values. Okay, I could make that 12 into 100 or 1,000 or whatever. It doesn't change the median. So what's happening right at the center is all that the median cares about. I guess think about it this way. What's right at the center is all the median cares about. The average is affected if we change these extreme values. So that changes a little bit how we think about or interpret those two things. And in general, we have this relationship between the two. So if the data is symmetrical, the average is equal to the median. So that looks like things like this. Trying to draw that to be symmetrical. So if you have something like that, a lot of times we'll look at histograms for things which are not bars. So far, everything I've drawn is bars, but the book and other things will have things that are curves. A famous one looks like that. That's the normal curve, and we'll talk about that in chapter 5. But it's symmetrical, so you can think about average and the median there. One way to think about the average, again, is that it's the balancing point. So this balances like sort of right in the middle. And it's also true that half the area is on either side. So I'm trying to draw a bar or a vertical line here that splits the area into half, right? That's where the median is. So if you think about a histogram, 50% of the area should be on either side of the median. It should balance at the average. So here also, I'm trying to draw that as a balancing point. if I've drawn it reasonably well. Also true that 50% of the area is on either side. Okay, so if we think about something that's not symmetrical like that, sort of two ways that it could look. One is that it has a long, well, there are lots of ways, I guess, but the main things I'll talk about are long right tail. Sometimes people will say skewed to the right. So that might look like this, might look like this, my little income example I did before. So in those cases, it's going to balance to the right of the median. So it's still true that half the area should be on either side of the median. So maybe that's, I don't know, around here or something. And it's not always like drastic, but the average should be a little bit to the right there. There's some extreme stuff that's going to have an effect on the average, but not the median. Just like here, when I move this value up to 12, the average is going to go to the right a little bit, but the median is going to stay the same. So here, if I sort of stretch things off to the right, the average goes a little bit to the right. The median still has half the area on either side. Here, with my sort of hypothetical income data, I said 50% in this bar, 50% in this bar. Okay, so that's where the median is. The average, the balancing point, should be a little bit to the right of that. Okay, long left tail looks like the mirror image of that. Oh, I'm sorry, I guess I didn't write down what I said. Average is bigger than median for these cases. And long left tail, average is smaller. So, you could have something like this, maybe a triangle, anything that sort of looks roughly like that, okay? So maybe that's about half the area on either side. The average is a little bit smaller. And maybe I'll just leave you with a couple of examples. I actually want to talk about the average and the median a little bit more on Tuesday, but I won't keep you. Long right tail, things like income, number of pets, cell phone usage. Anyone else have any examples of things that might have long right tails? Housing prices tend to have long right tails. A lot of things that have to do with money tend to have long right tails. But long left tail. Any thoughts on long left tails? Grades. Yeah, grades is a common example of something that has a long left tail. If you think about things that sort of have a natural cutoff at some large value, like the SAT scores of the people in this class probably have a long left tail. SAT scores of students in general might be roughly symmetrical. But for smarter students that get better test scores, have this cutoff, and so tend to have a long left tail. Okay, so I'll talk a little bit more about why we might use the average instead of the median in some cases and others, and last few little details about average and median on Tuesday. Okay, have a good weekend. Bye. Oh, you have homework due on Monday, okay? It's on BSpace. You have homework due on Monday.